Hey there, Chem Scholars. Today we're going to get into the idea of the Bohr model and energy levels and valence electrons. Okay, so the Bohr model was something you should have encountered over the summer assignment, but very briefly, Bohr envisioned atoms to be like our solar system. In our solar system, we put the sun in the center and the planets moving in almost circular orbits around it. Okay, Bohr felt that elements would do the same thing, but instead of the sun, we put the nucleus in the middle, and electrons move in rings around it. Okay, so he referred to those rings as energy levels. So, and he'd use the letter N to represent it. So N equals 1 would mean the ring closest, or the energy level closest to the nucleus. N equals 2 is the next one, etc. Okay, we'll talk about the idea of energy later on. But that's the basic model that Bohr came up with. Now, the Bohr model worked tremendously for hydrogen and not so great for the other elements because, well, other elements have more than one electron, so it was a little complicated. But it serves as a good model for us to start with, and we'll evolve from there, okay? So we're going to pretend that this model is the model for now, just to keep things simple, okay? Now, it's important to understand that energy levels are mirrored on the periodic table, okay, by the periods, okay? So you notice that hydrogen and helium are the only two elements in period 1. They only have one energy level. Then in the second row, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, okay? They're in the second row. That means they have 2 energy levels, okay? And so on down the line. So if I go to, the 5th period, then these elements here all have 5 energy levels. Okay, 1, 2, 3, 4, 5. So again, going back to this idea of the rings, okay, so something like rubidium is got to have some electrons in this first ring, some electrons in the second, third, fourth, and then the 5th, it'd have 1. Okay, so that's the idea of energy levels. Okay, so it's easy, if I were to ask you a question like, how many energy levels does tungsten have? All you got to do is look at the periodic table, find tungsten, and say, well, tungsten's in the 6th row. It's got 6 energy levels, okay? So, very easy, same idea. So nitrogen, find it, how many energy levels? Tin, find it, how many energy levels? Notice, okay, I wrote the names, but the periodic table has only got symbols. I expect you to know names and symbols. That's why I do this all the time. So try to get used to these. Okay. And of course, then tungsten we said has 6, nitrogen has 2, and tin has 5 energy levels. Okay. So now we have to talk about this term called valence. Valence is the highest energy level. So a moment ago we said that tungsten had 6 energy levels. Okay. So if tungsten has 6 energy levels, then the 6th is its highest one, meaning it's the furthest from the nucleus, it's the outermost, and we call that its valence energy level. So this one out here, okay, for tungsten would be its valence, whereas nitrogen only had 2, so it would go 1, 2, so the 2nd is its valence energy level. So again, the periods of the table kind of tell you where its valence is, okay? So the fact that tungsten is in the 6th period means its valence energy level is the 6th energy level. Okay. Now, keep in mind, Mendeleev did not know about the existence of electrons. Okay. So this table was set up before that was known. Okay. Kind of makes it a little bit more impressive when you think about it from that point of view. Okay. So now we're going to talk about the idea of valence electrons. Okay. So valence electrons are how many electrons are in the valence, are in that outermost energy level. Okay, and for this, we're going to use something called the octet rule. Oct meaning 8, right? So 8 is the maximum number. Now, if you look at the periodic table, there are 18 columns. How do we deal with that? Well, when we're counting over, we don't count the transitional metals. Okay? Transition, remember, that means that they're between energy levels. So they're not going to be counting towards valence electrons. So if we skip this whole segment in here, we're only talking about these 2 elements, and then these 6 elements, and 2 and 6 is 8. So to find valence electrons, really all you have to do is count over, but don't count transitional metals. Okay? So let me switch views and explain my point here. Let's talk about tungsten again. We said that tungsten valence is a 6 energy level. So I come over here and I count over 1, 2. Now I don't count these, but I hit tungsten as I go through. So tungsten only has 2 valence electrons. Even though it's the 6th one in, it only has 2 valence electrons. 2 of them are in the 6th energy level. These are in different energy levels. They're actually in the 5th or possibly 4th. And I'll eventually kind of talk about that. Okay? So we mentioned nitrogen, which is up here. So it's in the 2nd energy level, 2nd period. We count over 1, 2. We don't count any of these. 3, 4, 5. Nitrogen has 5 valence electrons. Okay? Talk about tin. We said tin is in the 5th energy level. So its 5th energy level is its valence. Then we count over 1, 2. And we don't count these. 3, 4. Tin has 4 valence electrons. Okay? So it's really easy to just count over. You just got to think of it as, like you slide through the transition. So 1, 2, slide. 3, 4, 5, 6, 7, 8. Okay? All transitional metals, for now, we're going to assume have 2 valence electrons. That's easy then. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay? So very, very easy to find valence electrons. So let's try a few. And by let's, I mean you. All right, so sodium, potassium, fluorine, chlorine, scandium, aluminum, antimony, gold, germanium, krypton. Find them on the table, get used to it. So sodium over here, potassium over here, fluorine, chlorine, scandium. We got aluminum, antimony, germanium, and krypton. Germanium, krypton. Okay? So just do the counting. Okay? Sodium, well, the first one, it's in column 1. 1. Potassium, same column. 1. Okay? Notice that. Sodium, potassium, both have 1 valence electron, and they're in the same column. Well, they're in the same family. Families share properties, similar properties. So it makes sense that sodium and potassium would have 1 valence electron because they should have similar properties. Let's go to fluorine, chlorine. Well, they're both over here, right? So fluorine, count over 1, 2, 3, 4, 5, 6, 7. Chlorine, 1, 2, 3, 4, 5, 6, 7. Again, same family. They should have the same number of valence electrons. Okay? Now, here's the rule breaker on that, though. Let's mention it real quick. Helium. Helium does not have 8. You go to the first row. There's only 2 elements. 1, 2. And again, that's why helium is often put above beryllium, because it only has 2 valence electrons. But again, by properties, it really does fit in with noble gases. Other than that, because the first energy level can only hold 2 electrons. That's what makes that a little different. But we're not worried about that now. Okay? Scandium. 1, 2. We say 2. Okay? Transition metals, always 2. Aluminum. 1, 2, 3. Aluminum has 3. Antimony. 1, 2, 3, 4, 5. Just like nitrogen, because it's in the same column as nitrogen, same number of valence electrons. Oh, I skipped gold before. Well, gold right here is a transitional metal. 1, 2. So it's just 2. Germanium. Okay, we talked about tin. You notice they're in the same column. Well, we said tin had 4. Germanium's going to have 4. 1, 2, 3, 4. And then we have krypton. All right. So, Superman, home planet. Let's count them off. 1, 2, 3, 4, 5, 6, 7, 8. Noble gases have 8, again, with that exception being helium because reasons, special reasons. Okay? Now, we're going to talk about a way to represent valence electrons as the last part of this. So let me change views and turn this around a little bit. And go to there. Okay. So I'm going to have to move the camera at times. You're good. You'll figure it out. Okay. So let's talk about one of those elements that we just did. For example, I don't know. Let's talk germanium. Okay. Germanium has 4 valence electrons, we said. Okay. So let's actually go talk about that idea for a second here and talk about something called, well, actually, let me switch views for a moment. Okay, electron dot structure. Okay, sometimes they're called Lewis symbols or Lewis dot diagrams. Okay, an electron dot diagram is a way of representing valence electrons as dots around the chemical symbol of an element. Okay, so technically there's 2 ways of doing this. We're just going to pretend there's one way, so don't even worry about those terms. Okay, we're just going to talk about a very simple way of representing them. Okay, so let's talk about germanium again. So germanium, its symbol is Ge. And we said that germanium has 4 valence electrons. Okay, so what we want to do is think of the chemical symbol as being a 4-sided thing. We have a top, bottom, left, right. And at most, any side can have 2 electrons. Remember, we said before, the number of valence electrons would be 8, so 2, 4, 6, 8. So that's how we're going to treat it. But electrons are negatively charged, and negatives don't like other negatives. They repel one another. So when possible, we always try and spread out the electrons. So as we start adding dots, wherever you start, and it doesn't matter where you start, we're just going to go 1 dot. So we go 1 dot, 1 dot, 1 dot, 1 dot. So there's germanium. 4 dots, 4 valence electrons. That is the electron dot structure for germanium. Now, let's talk about krypton. We say krypton had 8. So again, start where we want. 1, 2, 3, 4. Now I have to go back and start pairing up, and now I go 5, 6, 7, 8. So krypton has all 8. Okay, let's talk about something like fluorine. We said fluorine had 7. 1, 2, 3, 4. Now I start pairing up. 5, 6, 7. Does it matter which one is unpaired? No. As long as there's 1 unpaired and 3 pairs, you got it right. Okay. Let's do. Let's see, what else have we done? Lithium. Okay. Well, lithium had 1 dot. Again, which side doesn't matter. Okay. Let's talk about gold. We say gold had 2 valence electrons, so we go 1, 2. Again, I emphasize the sides don't matter. So whether you did this, or this, or this, etc., doesn't matter. Okay? So what we're doing is counting them off. Let's do one more. Let's do antimony. Maybe actually zoom in a little bit so you can see that better. Oh well, hopefully you can see it. There's some more slides that I'll show you in a second. All right, so let's talk about antimony. We said antimony had 5 valence electrons. So we go 1, 2, 3, 4, and now we start going around again and pair up, so we have 5. So there's 5 valence electrons. That's all it takes for dot structures. Okay, so hopefully that makes some sense. You can do some on your own. As a matter of fact, let's jump down to an example or so. Nope, that's not an example. Oh, okay. Oh, all right. I guess I forgot to put those. Oops. We'll stop the video there. Bye.